Hello again. Right, let's continue. This is Fedham's method to estimate the stress increase at a certain depth. So Fedham has taken the Busnet's method and make it applicable for an area instead of a single point load. But the principle behind it is still from a point load. Right, let's look at it. This is Fedham's chart. If you don't like his chart, you can use his formula, but I gather it's better just to use the chart because it's easier. Right? On the y-axis are the values of the k, the coefficient. You can see here the value of the k, which you are going to pop into the equation here in order to get your stress increase. Q is simply the stress that's being applied on the surface, right? And as you can see here, on the x-axis is the value of n, which is L over Z. See here, this is L of your foundation, and that Z is the depth that you want to consider for the stress increase. And these curves that you have here are M. And what is M? M is simply B over Z. So one is the breadth over the depth, one is L, the length over the depth. Simple as that. You just read it off the K and pop it in here. Now, if, for example, if you have a footprint of a building that looks like this, a rectangle, and you want to know what is the stress increase at point P, right, at a certain depth, Z, say. So all you need to do is to make sure that you can divide this footprint, the building footprint, into equal squares or equal rectangles that have one of the corners touching the point. So what I've done here is that I have block A or rectangle A. The bottom right corner is touching point P, and measure this L, measure this B, or this B, this L, whichever one, it doesn't matter. Just standardize for the rest of your diagram here, and read off the chart. You get a increment of sigma Z by having this area on the point P, right? Then you repeat the same process for the second part of the area, that is B and C and D. So you have 4, A, B, C, D, you have 4 delta sigma Z, am I right? Because you read off the charts 4 times to get this increment because of each individual rectangles. And you total them up, you get your total stress increase at point P because of this footprint at a certain point, at a certain depth below the structure. And see, so Fedham's method is very clever actually and easy to use. Right. And the next method that we are looking at is the pressure bulb method. Again, it has been simplified for you into a chart. As you can see here, this is for the square footing, this is for the strip footing. Just take a look at the square footing. This is a foundation here with the breadth of B. We are not interested to know the length of it because it's square, right? You can see here. Similarly, if we are talking about strip footing, we are not interested in the length because it's super long, right? So what we have here is that this is the location of the footing, and the horizontal axis here that you see, B, 2B, 3B, 4B, is the distance away from the edge of your foundation. Get it? So this is, sorry, not from the edge, from the center line of foundation. This is a foundation, this is a center line. So from this point to this point, B distance. From this point to this point is 2B distance. From this point to this point, from the center line of foundation to this point is 2B. From the center line of foundation to this point is 3B. Get it? Good. Okay. And what is the y-axis representing? This gives the depth of your of the soil. So depending on which depth you want to find the stress increase, right? And it again goes in the multiples of your B, 2B, 3B, blah blah blah. Okay, just notice this. If I want to know exactly beneath the center line of foundation, right? Say this is center line. I want to know when is that B depth from my from the base of my foundation. What is the stress increase, right? So I simply take this, draw a line from the center of the foundation down and cross it with, intersect it with B. So roughly it's about 0.4 Q. 0.4 Q, that's 40% of our stress. Q, that's the stress that you apply on top. So by the time you go down to B, the depth of equivalent to the breadth of your foundation, the stress has already reduced by 60%. See that? And imagine as it goes deeper, that's one. Going deeper, it gets less. What about spreading it to the side? Of course, when you apply a load on a certain surface, it is going to influence not just the depth, it's also going to influence on the sideways. The further away it gets, it's going to get smaller, right, the value. So it's proven by the pressure bulb diagram here. Look here. Again, let's just say at the depth of B, right? Now, I want it to be B distance away. So B distance away, I bring the line down. This is B. So roughly now, it has become what? Approximately, at this point, if I can do it again, B is here, this B is here, so roughly at this point, I follow this bulb down, it's about 0.08 Q. So when you're at depth B and at B distance away from the center line of formation, your stress increase is just 8% of the stress that you apply on the surface. So this has been summarized for you in a diagram here. You can see similarly, this is the horizontal distance away from the center line of your foundation, and this is for depth D equals to B, this is for depth equals to 2B, further down. Alright, square footing, strip footing is corresponding to the previous diagram. So just look at the square one. As you go further away, when D is equals to B, right, you are considering a depth that is at B, distance away from the base of the foundation. You can see that, as we discussed earlier on, right at the center line, right beneath the foundation, is just 40% of Q. But if you go B distance, away from it, you can see that it comes here. This is barely 0.1. Am I right? That was the 0.08 that we saw earlier on. By the time it goes to 2B away from the center line of the foundation, it is barely there anymore. Am I right? Barely there. It says what? Maybe barely 1 or 2%. You can see that? So that is a diminishing effect of sigma Z. Okay? As you can see, when you are taking D at 2B, it's getting even smaller. Right? So now you can grasp why it's important to put your foundation deeper into the ground so that it can sustain the bigger load because it's stronger. Number 2, because the stress distribution is diminishing with that. Alright, and the last method we're going to look at here is what we call the 1-2 method. The 1 is simply talking about, the 1-2 is referring to a gradient actually, 1 horizontal against 2 vertical, so it's easier to remember because some books will say it's 2-1 method. It depends on whichever book you want to look at, but the gist of it is that you're going to draw a slope going down at the gradient of 1 horizontal to 2 vertical, that's all. Okay, and what you're seeing is actually a trapezium cross section, am I right? Yeah. So when you bring it down, it's actually transferring the load to a greater depth and for a bigger surface. And see, and when you do that, what you are getting is a load divided by a larger surface. Hence, it's going to be a smaller value, right? And you do not have to calculate part by part for each trapezium. It has already been derived the formula for you as such. Alright, okay, that's about stress distribution. Now we move on to look at settlement. Alright, now for settlement, we cannot run away from odometer test. That's a standard, most common test that we conduct in the lab from the soil sample that you pick up from the site to estimate the settlement magnitude and also the settlement rate. Okay, this is how it looks like. Some of the groups may have already done the test, so maybe you can PM each other, I don't know, to exchange information about the test. So this is the odometer test setup. And let's take a look on the details of the odometer cell. That is the main bit of it. The frame is just simply a situation where a contraption, where you have a lever arm, you pop load here because there's an arm, and we know because of moment, right, you have a load over a certain distance, it exerts a bigger load onto whatever that is you're popping up there. And there's a counterweight here. This is a LVDT, a displacement transducer. This is a logger. So probably the one you have in the lab is a dial gauge one, I'm not very sure. Okay, so when you load it up here, you put the loads here, the load is being transferred through the lever arm onto this loading yoke onto your soil sample. Alright, this is a cell. So essentially you have a bath. It's usually made of brass, or some are made of thick perspex, stainless steel. It depends. The one you have in the Pago lab is made of brass. Shiny, looks like shiny gold. And we call it the bath because that is where you're going to put in the water. Remember, you put your soil in a ring and you put it into the cell, and before you do that, you actually put the porous stone at the bottom, and you put the soil in, and you put another porous stone at the top. You put in the loading cap, and then you fill it with water. You remember doing that? Why do we fill up the cell with water? Because the first assumption of an odometer test is that the soil is fully saturated. And if you recall, you may see air bubbles coming up when you first pour in the water, right? So that shows that the soil still has a little bit of air voids in there, and when the water is in, it could actually penetrate the soil and start filling it up. So the first assumption is being fulfilled, that the soil is fully saturated. Now you may ask, why? Why must the soil be fully saturated, or we assume to be fully saturated? Because we know no soils can be 100% fully saturated. There will be some tiny voids that will be still filled with air. it has to be assumed to be fully saturated, because when you start loading up the sample and the soil will just go down, right, that settlement, it will not go sideways because it is being confined in the ring. Alright, so all the movement, all the displacement is going downwards. So when the soil is going downwards, it's settling, the height is reducing. The reduction of the height is equivalent to the water that's coming out. Can you get it? It's equivalent to the water that's coming out. So imagine if the soil contains so much of air, alright? So when you compress, when you put the load and the soil is compressing, you don't know how much of the settlement is because of the removal of the water and how much of it is because of the air. And how are you going to calculate that? Can you see that? Yeah, so that is the first assumption, right? And of course, air is a lot more compressible and a lot more difficult to quantify. Okay, so now let's look at the results you actually get out from the odometer test. Those who have done it, that's probably lucky you will have got a graph like this, or maybe you don't. First attempt, maybe rarely we get a graph like this. You have plotted the height of the settlement or the ratio of the sample against time, and notice that this is a semi-log graph, meaning that the x-axis is plotted out in the log scale, right? And you also will notice that the standard says when you do an odometer test, we usually load them out in multiples of 2, meaning that if the first load is 12.5, the next one will be 25, the next one will be 50, 100, and so on and so forth. They say why? I think the answer is obvious in the sense that so that it's easier to plot on a log scale later on for your compression curve. We'll see it after this, alright? So for every load that you apply, you are going to leave it generally for 24 hours, and this is the graph you're going to get, alright? And we usually call this a time plot because it registers the sample height, which records the settlement against time. There are 3 parts to this, as you can see. One is what we call the immediate settlement. Once you pop in the load, it will immediately get squashed down. And the second part, that's the biggest part, that is the consolidation settlement. And the last bit, the tail part of your curve, that's secondary compression. So we will try to go through this part by part on. Once you have done for each loading test, say from 12.5, 50, 100, and so on and so forth, you will start to take out the settlement at the end of each loading stage and pop it into this graph, what ratio or settlement or sample height against the stress. So at 12.5, say you get this number, you put it here. At 50, you get this number, you put it here. So by the time you get it all into this plot, you find that you get a nice curve like this, right? And this part, which is linear, is a normally consolidated line. We call it the NCL or virgin compression line. Alright. Now, how do we know what is the pre-consolidation pressure or yield stress of the sample? All you need to do is that first, find the most curved part of your plot, that is, and draw a tangent to it, right? And second step, you just draw a horizontal line crossing that point. Next, you bisect the angle. And after bisecting the angle, extend your NCL out, and the intersection of that point would be your yield stress or pre-consol pressure. Now you say, what is this point all about? This point tells you what is the maximum stress that the soil has sustained before you took it out from the ground. Alright? So sometimes we say that I took the soil from 5 meters down, so on top of it there are 5 meters equivalent of soil weight, correct? So if the soil's gamma is 20, so 5 times 20 is 100. But I get this value as, say, 200. So where is the extra 100 coming from? As we discussed earlier, maybe the ground in the area was in the ocean before this, so there was water pressure over it. Or maybe previously it was during the ice age, it was ice, glacier on top of it. So all these previous loads on the soil will leave an imprint on it. In other words, your soil will actually have a memory. Okay, we'll pause here for a bit, take a break, and we'll come back later. Thank you.